Welcome back to Numerical Analysis, everyone. Today is Wednesday, April 8th, and we're going to talk about controlling the error in Euler's method. So, up to now, we've seen the basic Euler's method. We've seen some extensions of it where you use higher order Taylor polynomials in order to project the solution further. But we haven't really talked a lot about the error in the method. The only thing we've really noticed is that as you decrease the step size in Euler's method, the error does seem to get less. But how can we use that fact to make the method sort of prescribable in terms of error? That is, I'd like to prescribe how much error I'm willing to tolerate and then run the method and have it make sure that it stays within those error bounds. Well, that's what we want to talk about today. And so let's jump right in. Um, just to review, the order D Euler's method basically works by taking a currently computed solution, and that's our time value Tn and solution value Xn, and projecting it forward one step by incrementing the time value by a time step we're calling delta t, and then by projecting the solution forward using the degree d Taylor polynomial for the solution. So there is some error in this because we're using the Taylor polynomial, which is an approximation for the exact solution, right? The exact solution, which we can just call x, evaluated at time t sub n plus 1, would be from Taylor's theorem that Taylor polynomial plus the remainder term. So that's what my r here represents, the Taylor remainder term. The value of the Taylor polynomial at Tn plus 1 is, of course, just Xn plus 1. That's how we do our projection. But we can work with the Taylor remainder formula here to have Euler's method sort of self-adjust and stay within prescribed error bounds. Let's call the difference between the exact solution and the computed solution the truncation error. Truncation comes from the fact that we're using the Taylor polynomial, which you can think of as a truncated Taylor series. If we had the Taylor series for the function, that would be the exact solution. And again, that truncation error is given by our Taylor remainder term. And here's just the formula for that from Taylor's theorem. Notice that it involves this constant c that's between Tn, the current time, and the next time step. And generally, that's an unknown value. The key ideas here are to set a single step error tolerance, which I'm calling tau. For instance, you could use tau equal 10 to the minus third. That would give you about three decimal places of accuracy. Although for more accurate work, you'd probably want something more like 10 to the minus 6th or even 10 to the minus 12th. And then work with the Taylor remainder term to find a step size that ensures that that Taylor remainder is less than your error tolerance tau. Once you find that step size, you can project forward using that step size, and the error will be less than your error tolerance. Okay, sounds reasonable, but there are some issues with that. First of all, as we pointed out, the Taylor remainder term depends on this unknown value c that's between the current step and the next time step. Secondly, the Taylor remainder term depends on the solution x itself, which we're right in the middle of computing. So, what do we do? Well, there's a heuristic here that turns out to be quite useful. Heuristic, by the way, is just a fancy term for a problem-solving idea that has some practical justification, but it may not necessarily be the most optimal solution. But we're going to see that this particular heuristic is going to give us a very much improved version of Euler's method. So the heuristic here is, since we don't know what c is, just make a best guess as our last computed time value. I mean, after all, that constant is between the current time and the next time step. Since we know the current time, let's just use that as an estimate of c. And then plug that into the Taylor remainder formula. So I've just replaced c by Tn here. And let's call that our estimated remainder. So I'm using an R hat here to denote an estimated remainder. Notice this is not in contrast to some of the things we've done previously in the course. We're not necessarily saying that this value here is an upper bound for the error. It's just an estimate for the error. The actual error may be bigger or smaller than this, but hopefully it's close to this value. And that's the idea here. So then our estimated error would be hopefully close to the actual error. And now we can compute everything because everything's based on known quantities up here. So to take an example, let's look at this initial value problem we've been working with. And let's just assume that after a certain number of steps in here, we're at a time value of 0.2 and a x value of 0.829. And let's use these ideas to try to project forward one step. So let's just use an order 1 Euler's method. So we need to compute that first degree Taylor polynomial for the solution centered at our current time value. And that's what I'm doing here. So hopefully this is getting familiar to you. There is our Taylor polynomial there of degree 1. Next, let's look at that estimated error term. So here, here's the general form of that estimated error for a first degree polynomial. Again, I've replaced my c by my Tn. We can work with the ODE in the usual way to actually expand this in terms of things we know. The second derivative of our solution is the derivative of the first derivative, and then just performing that differentiation, remembering x is a function of t, and using the ODE, we arrive at this expression for the second derivative, which we've seen before. So the second derivative evaluated at t sub n would be this, and plug in what we know for Tn and Xn, and we get this value for the second derivative evaluated at t sub n. And then that plays into our estimated remainder. So just go back here for a second. Remember, here's our estimated remainder. We just computed that value there, the second derivative at Tn, as 1.80785. And so I plug that 1.80 value in here, and I get finally my estimated remainder for this step of the process. And now we want to use that to say, well, how big of a step can I maintain and still be within my error bounds? So let's set a one-step error tolerance of tau equal 10 to the minus third. We want to find the step size delta t such that the estimated error in absolute value is less than my error tolerance. So I use my formula for the estimated error that we just came up with. There's my tau. And I can solve this now for delta t. We find that delta t is less than or equal to about 0.033261. Of course, delta t also needs to be positive. So what we're saying here is that any delta t value between 0 and 0.033261 is going to give me an estimated error that's less than 10 to the minus third. And that's what I want. So what I want to do here is just pick the biggest step that I can take while still remaining within my error bound here. And that would just be this upper bound here, the 0.033261. So we take our step size to be that value, and now we project the solution forward. The new time value is our current time value plus the step size. So that turns out to be about 0.23. And the new x value is our Taylor polynomial evaluated at the new time value. So I'm just using that Taylor polynomial we computed previously and plugging in my new time value for it. And that gives us a projected solution of about 0.80979. But hang on a second. There's a little bit more that we can think about here. The estimated error here is estimating the actual error in our projected solution. Now, if we have faith in that estimate, what we ought to actually do is add that estimated error as a correction to the projected solution. All right. After all, if I thought, if my projected solution were 0.80979 and I estimated an error of positive 0.05, I could add that in and I should get a better estimated solution. So that's exactly what we're going to do. Instead of just taking the projection from the Taylor polynomial, let's add our estimate in for the error and hopefully get a more accurate solution. So that's what we're doing here. I'm just plugging in, this is again just the Taylor polynomial projection, and this is that estimated error. You could get this in a couple of ways. Either plug our t sub n plus 1 value back into the formula for r sub n, r hat, which remember is this guy here. Or you could just realize that since we solved the inequality and then took the maximum possible value of delta t, we're going to get 10 to the minus third as the estimated error. And both those things work out. So you get a corrected solution of 0.81079. That's going to be a more accurate projection forward than if you had not incorporated the estimated error. Now, it's worthwhile to take another look at this from sort of a more general perspective. What are we actually doing when we add back in that estimated error? Well, I'm just writing out, again, the first degree Taylor polynomial and then our estimated error. And if you look at that, that's the second degree Taylor polynomial. So what this is saying is that when we add back in our estimated error, what we're actually doing is getting the second degree Taylor polynomial estimate for our solution. So the corrected first order method is going to be actually the second order method. But we also have more information. We have information about the maximum step size we can take while staying within our error bounds. So this is kind of an added bonus to this technique. So in summary, how does the adaptive order D Euler method work? Well, we're going to use the degree D Taylor polynomial to project the solution forward. We're going to estimate the error using r hat, and that just turns out to be that last term in the degree D polynomial. So the degree D term in that polynomial is your estimated error. You use that estimated error to choose a step size that stays within your error tolerance, and then for that delta t, you project forward using the polynomial. And notice the way that I've got things set up here, this automatically includes that estimated error term, because we're just calling it that estimated error term is actually already added in here as the last term. So let's take a look at an example. Let's take our familiar initial value problem here. We've been working with this guy all along, and use the adaptive Euler method of order 2 to compute a solution. We'll use a single step error tolerance of tau equal 10 to the minus third. And notice I don't specify a step size here, because at each step of the adaptive method, we're calculating the biggest step size we can take in order to stay within our error tolerance. So the first thing, as usual, is to compute the Taylor polynomial of the appropriate degree for the Euler's method. Our degree is 2 here, so we compute the Taylor polynomial of degree 2, and we've done this before. This is the guy here. The estimated error term is going to be this last, the degree 2 term in that Taylor polynomial. So that's it right here. And I've just multiplied through by the 1/2 here. And then I'm just going to, for notation's sake, call the t minus tn. That's our delta t, right? That's the step size we're going to take in the next step of the solution. Okay, with those two in hand, I'm ready to get going. Step 0, as usual, is just to initialize the method using the initial condition from the initial value problem. Uh, Step one, the very first thing we want to do is compute the step size. So we want our estimated error to be less than our tolerance. So here I'm using our formula for the estimated error. Here's our tolerance. Plugging in the values of x0 and t0 that we know, and you get this little inequality here for delta t. Solve it, you find that delta t is between 0 and 0.025820. So we're going to take, again, the biggest step size we can take while still remaining within our error tolerance. So that would be the 0.02582. And now project the solution forward. So the new time value is the old time value plus the step size. And the new solution value is our second degree polynomial added, evaluated at the new time value. And you see, this is, again, that correction term is already here. So this includes the correction term. So there's our T1 X1 pair for step one, and the process can continue. For step two, we again start by computing the step size. Now in my formula for the estimated error, I use X1 and T1, my most recently computed solution values. Error tolerance is still 10 to the minus third. We get this equation, we can solve it, and now we get a time step of about a little bit larger, right? 0.26705 as opposed to 0.025820. So the method really does adjust that step size at each step to take the largest possible step and yet still remain within the error tolerance. And then we project forward. Our T2 is the T1 plus the new step size, so there it is. And X2 is the second degree Taylor polynomial evaluated at T2, so that's this guy. I'm going to plug in my previously computed solution values for X1 and T1, and then use T2 here, this value of T2 here, and you do that arithmetic and you get 0.95147. And so the solution so far is tabulated here, and the process continues for as long as you need solution points. As usual, I've gone ahead and coded up this in MATLAB, and here is the solution for time t going from 0 to 1 for this problem using our order 2 method with tolerance of 0.001. And so you see, in fact, at this level of resolution, the two solutions, the exact solution and the Euler solution, are indistinguishable. They're very close. If you zoom in on the graph a little bit, you will see a discrepancy. Here it is. Again, the Euler solution here in color and the more accurately calculated solution in black. If you look at the gap between those two and look at our scale size over here, it's on the order of 1 part in 1,000. And so our error tolerance is being satisfied by the method. The method extends to higher orders, and just for curiosity's sake, I used an order 3 adaptive method with the same tolerance to solve this same problem, and here is the solution. Notice that for order 3, we could take a lot bigger step sizes because now we're using a Taylor polynomial of degree 3. And so the method correctly determined that to stay within a one-step error tolerance of 0.001, using order 3 polynomials, he could take larger steps. And so this is a pretty efficient as well as pretty accurate computation of the solution. And again, at this level of resolution, pretty much indistinguishable from the exact solution. If you zoomed in, you would see an error. It'd be about on the order of 1 part in 1,000. And you could decrease that by just decreasing your tolerance. And that would give you a more accurate solution. So the adaptive Euler method really incorporates sort of the fundamental ideas that are present in all modern numerical ODE solvers. I don't want to give you the impression that the adaptive Euler method is the last word in numerical ODE solvers. It's not. There are more efficient and accurate methods out there, but they all do the same kind of thing. That is, in addition to projecting the solution forward in some way using the differential equation, uh, they also keep track of the error that is present in each step and use mechanisms like adaptive step size or other mechanisms to keep that error in control. And so I thought it was worthwhile for us to take a deep look into the Euler method to at least get an idea of the principles that underlie other methods. In our next lecture, I'll do an overview of some of the sort of industrial strength uh, techniques and algorithms that are out there for solving ODEs numerically that really represent the state of the art right now. But for now, I think our little tour of Euler's method has given us a pretty good picture of the principles that underlie those methods. And so that was the whole purpose of us taking this sort of deep dive into Euler's method. Okay, there will be another homework. This will be due Friday. I guess it's homework 22 or 23 now. I'm losing count. I hope you all are well. As always, let me know if things are confusing, or if you have questions, or if you just want to say hello. Y'all take care, and I'll be back in touch real soon.